Hello everybody, Mr. Hasty here again. Today we're going to be talking about chapter 12.4, which is on phase changes. So phase refers to the states of matter. So we're primarily going to be talking about the standard states of matter, which are solid, liquid, and gas. And we've already talked about phase changes before. We have solid to liquid, which is referred to, of course, as melting. Liquid to gas, which we typically refer to as vaporization, boiling, something along those lines, but most of us refer to it as boiling, although that's only one type. You can go solid to gas, which is called sublimation. And we've witnessed that before with iodine and dry ice, going straight from a solid to a gas. We have the reverse of each of those. Gas to solid we haven't seen before, but that's called deposition. Frost is an example of deposition. Water vapor in the air coalesces to ice crystals on a surface. Gas to liquid is condensation. Hopefully don't run out of room here. And liquid to solid, referred to as freezing. Now, certain phase changes require energy. If we remember what temperature is the average kinetic energy of the particles of a substance. So, solids typically have less energy than their liquid state, which have less energy than their gas state. So if you're going from solid to a liquid, if you are melting, vaporizing, or sublimating, that requires energy. So to melt something, you have to heat it up. That means you're giving it energy. Vaporization the same way. When we've looked at sublimation before, when we heat the crystal iodine, it turns straight into that purple cloud that we see. And when we expose dry ice, which is frozen CO2, to a hot environment, to a room temperature environment, I should say, it goes straight into a gaseous form. So let's give a formal definition of the word melting point. So specifically for a crystalline solid, the melting point is the amount of energy required to break the lattice. Remember, the crystals have lattice structures, geometric structures, and turn to liquid. So we talk about crystalline structures here, and we've talked about how a large amount of the structures that we've talked about are crystalline. Sugar is crystalline. You can have network covalent crystalline structures, ionic crystalline structures, covalent and metallic crystalline structures. The other type of solid besides crystalline is amorphous, and the reason why we don't have exact melting points for amorphous substances is depending on the particular particles, it will melt at different temperatures. And so there's not one melting point. You can't say at this temperature and pressure, it's going to melt. So if we have our solid here, it's arranged with bonds in a lattice structure. If we can provide enough, now remember, all particles are moving. Those solid particles are vibrating around. If we give them enough energy, they will start to break out of that structure and they will start to move around each other. They'll still be attracted to each other by intermolecular forces, but now there's not in a fixed pattern. They're going to start moving. And that's what a melting point is. Now, it's important to note that I said at a certain temperature and pressure, because as we're going to talk about, especially next chapter, when we're talking about the phase of something, we're going to have to refer to both its temperature and pressure in terms of how it's behaving. Let's move on to our next topic. All right, vaporization. So vaporization is the technical term for taking something that is a liquid and turning it into a gas. Now, to vaporize something, if we have a liquid, we have particles that are pretty stuck together. That's why they maintain their volume. And if we give them enough energy, they will start bouncing around all over the place. And that is when they become a vapor. Remember, a vapor is different than a gas in that a vapor is something that is typically in a liquid state that has been turned into a gas. That's the technical definition of a vapor. Now, because substances tend to have lower intermolecular forces towards the surface. If you remember, water has surface tension, and that stems from the fact that the water molecules down below can attract in a lot of different ways, but the ones at the top can only attract in a few because they can't attract above them. This means that it is easier to break apart the surface molecules of a substance, and so it's oftentimes easier to break the surface molecules of water or isopropyl alcohol by evaporation. So evaporation is vaporization at the surface. So when we talk about water evaporating, it's because it requires less energy, the ambient heat, to make the surface water turn into a vapor. Now, before we move on, I want to talk about how vaporization and evaporation are usually going on within most liquids. And the reason for that is you got to remember that temperature is the average kinetic energy, which means that not every particle has the same amount of energy. So if you have a certain amount of water, the average kinetic energy of that water dictates the state, but enough of those particles in a certain region might have enough energy that they would actually be in the gaseous phase. And that's why you can have evaporation and things like that, even if the whole sample is a liquid. So when you evaporate something, it creates, or just vaporize something in general, it creates something called vapor pressure. And so vapor pressure is the pressure exerted by a vapor on its liquid. So, if we have a jar of boiling liquid, let's just say water, here's our liquid, and we boil that, it's going to have particles of gas vapor that want to get out. If they all can't escape, it's going to start building up pressure and exerting pressure downward on the water. Now imagine if we put a stopper in that bottle, it's going to exert a lot of pressure downward on that water. And that's what we're referring to as vapor pressure. Even if it could let some of it out, some of it's going to stay in there. Now, as vapor pressure builds up, the temperature at which vapor pressure equals atmospheric pressure is referred to as the boiling point. So to boil something, you actually have to raise the temperature such as the vapor pressure, the pressure being exerted downward on the substance, is equal to the atmospheric pressure. So if you're boiling a pot of water, initially you'll have some evaporation. You can see the steam rising off the top of the pot of water until the vapor pressure above it builds up enough to create a boiling effect. You don't get that effect. Even if the water is really, really, really hot at that point, you need that extra step of the vapor pressure equaling the atmospheric pressure. Finally, we're going to talk about sublimation. If you remember, sublimation is the process of going directly from a solid to a gas. Now, we have two things that we've worked with. We worked with frozen CO2, which is dry ice. And we've worked with iodine crystals. A couple other mothballs are something that sublimate. And air fresheners, actually, solid air fresheners. If you ever wondered how those work, they are sublimating as well. Different chemicals in those. So, what happens in sublimation? So, remember, if things are in crystalline structure, it means they're held together in a fixed pattern. Now, why would it be possible to break that solid pattern and go straight to a gas? Why are you skipping over the liquid step? So if you remember, there's a certain amount of energy holding those together, and if we push apart the forces, it might be that there's just not the right amount of energy to keep them held close enough together, so that essentially once you have enough energy to make them move, you have enough energy to make them move a lot. So by adding energy to that system, it goes right through the liquid phase and just goes straight into a gas phase where all the particles are flying around. All right, so the key thing to remember about the three things we talked about today, melting, vaporization, and sublimation, is that the process involves giving energy to the substance. These processes need energy. You might be like, well, evaporation doesn't need energy, it just happens. It happens due to the ambient energy in the environment, sunlight, heat, things like that. But all of these need energy. Okay. So tomorrow we're going to talk about the other types, the types that give off energy, and how all these things are interrelated. See you then.